All right, so anytime, as we said in the post-translational modifications, anytime we're going to activate the pathways that I'm going to talk about, we're not going to just do it as a linear way, the way that I'm going to talk about it. What we're doing is each step along the way, we're going from one molecule to multiple molecules to multiple more. So this is like what you guys have all seen all over the news with the coronavirus, is that a single individual can infect a number of other individuals who can infect another. And so you get this huge amplification in what you now know, exponential growth. So the exponential growth component, or signal amplification, is a component of any of the molecular pathways that are the phosphorylation pathways that we're going to just talk about. So a single molecule of IGF1 binding and turning on the first kinase is going to have this huge cascading effect. So let's keep that in mind, but I'm going to draw it as a single molecule to a single other molecule. All right, so what's going to happen is anytime you get a hormone like insulin or IGF1 that binds to a receptor, it has to have a cell surface receptor, and these are usually called receptor tyrosine kinases. Because what happens is you have two subunits of a receptor. When the hormone is there, it brings the two subunits together, and those two subunits together have what's called autophosphorylation event. So one of them is going to phosphorylate the other, and it's going to change the charge of a specific region within the receptor. And when that happens on the insulin or IGF1 receptor, what happens is that works like a magnet and draws this protein, the IRS1, or the insulin receptor substrate 1. As the name says, it's the first substrate, so the first downstream signal of the insulin receptor. So the IRS1 is going to bind to the phosphorylated sites that appear when insulin brings the two receptors together and causes autophosphorylation. All right, IRS1 comes up, and then IRS1 is going to serve as a scaffold protein. So a scaffold, just like we know of scaffolds in construction, it's a thing that kind of holds everything together so that you can build a structure. So what we're going to do is we're going to build a structure around IRS1. So IRS1 is sucked up to the insulin receptor like a magnet, and when it's there, it's going to have a magnetic effect as well on this protein P85. And P85 is part of this bigger molecule called the PI3 kinase, or the phosphoinositide inositol 3 kinase. So this is going to be a kinase that is not a protein kinase, but it's a lipid kinase. Phosphoinositol is a lipid that exists in the membrane. So this is a two-component kinase. One is the regulatory component, P85, and what that does is that determines which part of the cell it is. This active part of the kinase is in. Okay, so IRS1 is sucked up like a magnet, and when it's sucked up like a magnet, it becomes phosphorylated by the insulin receptor. It's going to produce new negative charges, which are going to bind P85. And when that happens, now P85 is together with IRS1. Where does this happen? Well, it happens at the plasma membrane because that's where the insulin receptor is. And now what you've done is you brought P85 and its friend here, PI3 kinase, up to the membrane because that's where the insulin receptor is. So really, P85 is like the ugly stepbrother, where the stepbrother gets invited to parties and everything because everybody wants the really, the really beautiful, attractive brother to come to their party. And so what they do is they invite the ugly one and they bring their handsome brother, and now at the party is the one that you really wanted, PI3 kinase, because now what it is right beside its substrate. It phosphorylates lipids. The phosphoinositides are lipids that are in the lipid bilayer. So they're protein and fat together, and what it does is it phosphorylates and makes PIP2, so phosphoinositide bisphosphate, into phosphoinositide trisphosphate, so PIP3. So all you have to know is that PI3 kinase converts PIP2 into PIP3. Okay, I denoted these as these little lollipops, the red one because it doesn't turn things on, and the green one because now the whole system is on. Just like we've talked about before, for every kinase, there's a phosphatase, and this phosphatase is P10. And what P10 does is it converts PIP2 back, or PIP3 back into PIP2. P10 is in red because it's going to stop the pathway. And it's also known to be a really important anti-cancer drug or anti-cancer target, because if you can convert PIP3 into PIP2, you decrease the risk of uncontrolled growth, and that's cancer. We want to drive growth from resistance exercise, so we want to make more PIP3. Okay, so basically, insulin or IGF-1 is going to bind to its receptor. You're going to dimerize the receptor. That's going to cause phosphorylation of the receptor. When that happens, the negative charge of the phosphorylated receptor brings IRS1 up. IRS1 gets phosphorylated. It brings P85 up. P85 is always going to bring PI3 kinase with it. Now, all we've done, the whole idea of insulin binding, is to bring proteins to the membrane. We bring proteins to the membrane because now the substrate for PI3 kinase is in the membrane. You phosphorylate PIP2 into PIP3, and now we have this downstream signal for driving the next phase of the response.